Week 6, problem 10. Alright, so this is the big circuit analysis problem that you guys are going to do. You'll probably see one like this on the test. And it'd probably be good to get an idea of how to do this well. Alright, so first thing you do when you look at this is like, alright, can I combine all these through parallel and series? So I'm going to start by redrawing this guy. So we can combine these two resistors, R2 and 3, and then these guys, and then can't do anything with that guy. So I'm going to draw this one. This guy will be R1, which we know is 9. We're going to do another one right here. That's going to be the 5 and the 1. Put those together, we're going to come up with 6. And we're going to have a battery, which is 4. Then we're going to have another battery, 4 volts, which they tell us is, do they tell us what that one is? They probably, yeah, 15.0 volts. I can do a better 5 than that. 15.0 volts. And then we have R2 and 3 together, which is a total of 6. Alright. So at this point, we can't really do anything else anymore combining. So you might be like, oh hey, there's 2 batteries here, I can combine the 4 volts and the 15 volts. Well, no, because you'd have to split this 4 volt battery between part of it here and part of it there, and you don't know how much would have to go to each side. So you can't combine those. No, that's all you can do for this portion of it. And now we're going to have to use Kirchhoff's voltage law. So here it basically tells us to find everything, all the currents, left, middle, and right. This is going the energy. This is more energy. We're basically going to have to solve everything. So from here, idea of Kirchhoff's voltage law is that you can, if you go around a circle, you add all the voltages, voltage rise and voltage drops. And when you get back to where you start, you're going to end up with 0. So I'm going to switch this guy to blue, mostly for contrast, but also because, you know, I like blue. I get tired of it and switch to red from time to time, but, you know, I still like blue. This guy is going to be IR for middle. This will be IM. Ooh, IR for right. IM for middle, and IL for left. Did I forget the I's? I forgot the I's. I always forget about I, me, something. Alright. So, we're just going to start drawing loops. Yep, it looks like we're at the loop drawing stage. I'm going to draw the first loop in green so we can see where I'm drawing. So I'm going to start here, and I'm going to change the direction of this guy. So I'm going to say that this current actually goes down. So current comes out of the battery like this, current comes out of the battery like this, and current comes down and then goes to each of them. So going back to the awkward green, I'm going to do this loop. I don't like to go through batteries backwards. You can, it just means instead of using a positive number, use a negative number. Alright, so we also know Ohm's law. Ohm's law is V equals IR. So that's how we're going to be converting between voltages and currents and resistors. So the way I set this up is I start here. I'm going to start here. I'm going to go through the first resistor. So we're going to have a voltage drop of IR. Yes, I'm going to do it here. IR, and we're going to multiply that by 6. So I'm going to say 6 IR. Okay, then it comes over here along this loop. It's going to then pass through this resistor over here. And if you're going along, following the current direction and the resistor, then it's going to be like a positive times a positive, and you're going to get a negative drop. What I'm saying is that if you're going the opposite direction of the current, then instead of having a voltage drop, you'd have a voltage rise. So whenever possible, have your circle with the battery follow along the same direction of the current. It just makes it easier. Alright, so then we're going to have 9 IL for left, and then we're going to have 0 I middle. Okay? And then these are going to be equal to the voltage rise as we go across the battery. Now your first question might be like, oh, why are you writing this awkwardly? You'll see in a second. This will make it a little bit easier. Alright, so now we're going to do another loop. I'm going to use another color. Ooh, I don't think I've ever even used this orange color. I'm going to go loop like this. Hop, hop, hop. There we go. I'm going to go through this one a little bit quicker. I'm going to write the IL first. So I know it's going to go up and around and over like this. I'm going to do the IL first because it'll be easier for me to keep everything clean. Then I'm going to write this part right here. It's going to be 6 IM plus 0 IR. I actually include the 0 in there because you'll see in a sec. And this will equal 4 volts. Alright. Now your next thought would be here, be like, alright, let's draw another loop, and then we'll have 3 unknowns, 3 variables, and we'll have everything we need and we solve. Well, I'm going to try that just to show you that it doesn't work. It doesn't work like that. Alright, so what we have then is, let's see, here we would have 6 IR. We would have, so this would be going against the current, so it would be negative 6 IM. And we'd have negative 4 V. We have 0 IL. And we would have, we could be going against the battery, so this would be 15 minus 4, which would be 11 volts. Right. So when you look at this, you're like, oh, okay, 3 equations, 3 unknowns. No, you only have 2 equations. These are not linearly independent. So if you took this equation minus this equation, you'd get this bottom equation right here. Is that right? No. Yes. Yes, it is right. Yes. We get this bottom equation right here. And when you have non-linearly independent, it's not going to work. You're not going to get an answer. At least nothing that's going to be useful for you. So, any of you guys that have taken matrix theory yet understand this. The other people are like, well, I don't understand, blah, blah, blah. That's okay. Just follow the method. Follow the method. You're going to probably get one question like this on an exam, and if you can just kick the daylights out of it, your life will be easier. I mean, less points you have to get on the rest of the exam. Right, so the other equation we're going to use is Kirchhoff's current law. So I'm going to use Kirchhoff's current law right at this point, right here. So Kirchhoff's current law says that all the currents coming in equal all the currents going out. So I would be able to say that IM, which is going in, plus IR, which is going in, would equal IL, which is going out. IM plus IR equals IL. Or, in other words, I'm going to say that IL minus IM minus IR equals 0. Okay? So then this becomes IL, 1 IL. Make it a little 1. Ah, that's a terrible one. I'm just going to draw a straight line. There we go. Minus IM, minus 1 IR, equals 0. Alright, so now I'm going to rewrite this in a slightly more compact notation, which you will see why in a second. So this is going to be 90615. This is going to be 9604. This will be 1, negative 1, negative 1, 0. You can put this into your calculator and solve. So the way I'm going to do this then is I'm going to Google matrix solver, Gauss-Jordan elimination calculator. Bam! Thank you, Gauss-Jordan. I think that's just the method, not the actual guy. So it is 3 rows by 4 columns. Set matrix, okay. So we have 9, 0, 6, 15. So 9, 0, 6, 15. And then the second row will be 9, 6, 0, 4. 9, 6, 0, 4. And last one will be 1, negative 1, negative 1. 1, negative 1, negative 1. Fill empties with zeros. And then solve. Now, I want a very detailed solution, just so I can... Did I just ruin that? Oh no, come on, you're killing me. Ah, darn you, schmalls. Okay. 9, 0, 6, 15. 9, 0, 6, 15. 15. 9, 6, 0, 4. 9, 6, 0, 4. And also 1, negative 1, negative 1. There we go. 1, negative 1, negative 1. Fill into a very detailed solution. There we go. That's not more detailed at all. That's okay. So what that's called, what it will show you on your calculator, what you do is figure out how to go. You probably have a TI-83, and you can go in there, and what you want is make it to use linear algebra, matrix multiplication, to put this into row reduced echelon form. It'll probably be RREF. So what that does is it simplifies it, so you get this. The triangle, that's echelon. Row reduced, it means row are reduced as much as they can. And then these answers you have here, 19/24. I don't like 19 divided by 24. 0.79. Okay, the next one we have is 25/48. 0.52, okay. And then the last one is 21/16. Which is 1.31. And this guy was supposed to be negative. Perfect. Alright. So now, this says that IL, which is the first one we had, is 0.79. 0.79. There we go. And since it's positive, that's saying that the direction we chose was correct. I chose wisely, or some such as the, Indiana Jones. Chose poorly? Chose poorly. Chose wisely. Anyway, IL, so IL is down, because we chose it to be down and it was positive. Okay? Next one will be negative 0.52. So the magnitude of negative 0.52 will be 0.52. And we said it was going up out of the battery, but actually it's going into the battery. So it's also going to be going down. So what happened was this 15-volt battery is so much more powerful than the 4-volt battery that not only is it able to go through the resistor, but it also powers through the battery as well. And then the other one is 1.31. 1.31. I have complete faith that you guys could use algebra and solve these equations. I would recommend using your calculator, especially if you have like a TI-83, because you're pretty much guaranteed to get a problem like this on exam. If you do this, you'll be able to save a little bit of time, it'll be more accurate, and you'll be able to use that extra time on other problems. So spend a little bit of time, figure out how to do it. Google row reduced echelon form, TI-83, YouTube video, whatever. It'll show you how to do it, how to put the numbers in your calculator. Yeah. And we basically solved for everything we need for the currents at this point. So now we're just going to go through and figure out how to answer each of their questions. So find the energy delivered by each battery. Okay? So for the battery, I'm going to use P equals IV. So for the first battery here, we're going to have 15 volts times the current, which will be 1.31. So 15 times 1.31. And we have, what, like 21, 22? Oh, times 19.65. So that's for the second part here. So this guy will be, why is it asking for it in kilojoules? Ah. So, sorry. This is asking, I found power, and what it wants is energy specifically in joules. So power is IV, it's 19.65, 19.65, which is joules per second. So I'm just going to straight up convert 3.5 minutes into seconds. 3 minutes is 180 seconds, so this is going to be 210 seconds. So I'm going to take this 19.65 and just multiply it by 210. Which gives us 4.13, 4.127. 4.127. I could kind of make that work. Not really. And that's how many kilojoules it has. So I took the joules per second, which is a watt, and multiplied that by the number of seconds, which was 210. I think it's 210. Yeah, close enough. Alright, so now we can do the same thing for the 4 volt battery. Take this guy's the 15. So I'll call this guy P4, which will be 4 volts times I middle, which is 0.52. 4 times 0.52. I can do that one in my head. What's like 2.08? Yeah, I'll take 2.08. And that's joules per second. So I'm going to do 2.08. 4 times 0.52 times 210. You can see I'm not actually that confident with my math on that one. 436.8. 436.8. 436.8 joules. Perfect. Alright, now we need to find the energy delivered to each resistor. Okay, we can do this too. Not too bad. Let's hope not. We'll see. Could be tragic. Could be tragic. Alright, 8.7 ohm resistor. I missed. I'll say that that's a 9. Yeah, we're just going to switch that with a 9. So, for the resistor, I'm going to do I squared R. Whoop, I squared R. Go away. Oh, there we go. Do they just want us to do it for every resistor? Because it might be. I'm just going to assume they want us to do it for every resistor. Alright. So for R2, it's going to have 3. So R2 would be 1.31, which is the current. 1.31 squared, and then we said it was R2 is 3 ohms. So I squared R is 1.31 squared times 3, which is 5.15. 5.15. I'm going to change one thing real quick to backtrack. So this guy is going up. And the current is actually going into the 4 volt battery. So energy is not being delivered by the battery, it's being delivered to the battery. So I'm going to call that actually negative. Because if you look at the P equals IV equation, the current I is negative, voltage is positive, therefore the power would be negative. And that's one of the reasons why when you're talking about power, for like batteries or motors or generators, you have to use the power equals IV equation, not the I squared R. Because if you used I squared R, the negative would disappear, and you'd lose that information. Ooh, I was going somewhere. 1.31. Yep, got it. 5.15. So R2. Yeah, I'm gonna call that 3. Do we have 3? I gotta say it's 3. Yeah. I'm gonna say this guy's 3. Up. 3. That guy. 9. 9. There we go. So for the 3 ohm resistor, we have 5.15. For the 9 ohm resistor, R1, we're going to have, left branch is 0.79, so we're going to have 0.79, 0.79 squared times 9, and that gives us 5.6. The 5 ohm resistor. 5 ohm is in the middle, so it's going to be 0.52 squared. 0.52 squared times 5. And that gives us 1.35. And then we're going to have a 1 ohm resistor right next to it. So it's going to be 0.5 squared times 0.1, times 1, which is basically 0.52 squared, which is 0.27. This guy's getting tedious. 0.27. Okay, one more. Time to rally. And the 3 ohm resistor. I'm going to say it's that one. Oh, is it the same as R2? Nice. So it's going to have the same current as R2, and therefore I'm just going to say it's exactly the same as it. Bam, because they have the same current going through them, the same resistor, the same. Alright, identify the type of energy storage transformation that occurs in the operation of the circuit. Okay, so this thing here is we have current going from one battery and going into the other battery. What that is charging the battery. We are charging the battery. It sounds like a legal term where you battery and charging, but no, completely different. Why do they have so many similar terms? Maybe there's a reason for that. So, find the total amount of energy transformed into internal energy in the resistors. Find the total amount of energy transformed into internal energy in the resistors. I'm going to see what that means by internal energy. Internal energy. Maybe there's some within the system, excluding kinetic energy of motion, potential energy of the system as a whole due to external. Okay, so what we're going to say then is the resistors, the energy transformed by the resistors is transformed into heat, I squared R losses. So what we're going to do is we're just going to add up all of these. 5.15 times 2, because we got 2 of them. Then 0.27 plus 0.27 plus 1.35, 1.35 plus, and then what's the last one? 5.6. And we get 17.52. That makes me skeptical. Oh. never mind. Okay. So what I did wrong with these guys is this is the power delivered by each of these. So we need to multiply it by the time, which is 210 seconds, 3.68. So then for this guy, for the total, it's going to be 3.68. Now, if I was a better person, I'd go back and I would recalculate all these. I'm not going to. You take this number, so multiply by 210 seconds. So these are all measured in watts. Coming down here, this is measured in seconds. We do multiply watts, which is a joule per second, times seconds, you get joules. And that's why we should get much larger numbers. So, and then the total will be 3.68 kilojoules. That's what I did wrong with that guy. Same mistake I made back here with the batteries. Okay? So the trick to this problem is Kirchhoff's voltage law. That's where the difficulty here comes. I recommend setting it up in a matrix, putting that matrix into your TI-83 or TI-83 plus, whatever equivalent calculator you have, and then do matrix, I guess probably operations, and look for RREF, row reduced echelon form, which will give you each of these. So the key here is then just to kind of know this method. You don't need to know matrix theory, you don't need to know linear algebra, just know this method, YouTube it a couple times, walk through it at least once, probably twice, get the answer, and that way when this comes up on the test, which it will, you'll be able to crush it like a small, I don't know, piece of fruit, a small piece of fruit, like a tomato. Alright, sounds good? Alright, see you on problem 11.